Welcome, everybody. So this is 719 Mathematical Economics. Today, we're going to start discussing discrete time dynamical systems. So up to this point in this semester, we studied the continuous time systems. Now, we define time as a discrete variable. So time is again defined with respect to some history, right? So this is a set, and this set is now a subset of the set of integers, okay? Typically, we look at such an history, all right? So there's this initial time, t equals 0. Then time passes one period at a time, and then typically in economic models, we look at infinite horizon economies, but the economy could have a finite horizon in some models. And in general, the entire set of integers could be our history, okay? And again, as in the continuous time systems, we are interested in some variables that change in time, okay? So in general, these variables will be real valued. So for each t, there will be a particular x value that is typically a real valued variable. So that's typically a real number. But then we can also study, of course, vectors, right? So this has I mean, there's no problem in studying the vectors. So if I define xt in this way, so what I basically mean is, once again, a vector of variables that change in time, okay? And for most of, so in this week and in the next week, we'll be basically interested in systems like this. So there will be two variables that change in time, and how they change will depend on their existing values at t, right? So there is this, so these are now transition functions. And we want to understand, of course, in the most general case, I can actually write this even more generally by making these systems non-autonomous. Okay, so these functions themselves may change in time, but then again, there is a simple way to make a non-autonomous system and an autonomous one. I will show you that. So in general, this is the system, this is the type of the system that we are going to study. Once again, we're going to find steady states, and we're going to find linearization of such models, and then we study the type of equilibrium. All right, so we're going to look at the eigenvalues of the linearized system again. So most of the stuff is pretty much similar to what we have done for the continuous time dynamical systems, with some important differences, and I will of course underline what these differences are. Okay, so to start with, let's look at the scalar dynamics. All right, so let's look at only just one variable, and let's define this difference equation. Okay, and I will tell you that, so time starts at 0 and extends to positive infinity, and we have this initial value that is given, right? And f is some nonlinear function. Now, obviously, we define the steady state, or the set of steady states, in this way. So a typical element is x star, okay? So that typical element should satisfy, of course, this equation, right? So any x star that satisfies this equation, in other words, any x star that is a fixed point of this equation will be a steady state. Now, once again, of course, we talk about the existence, uniqueness, and the stability of such steady states, right? Existence is basically whether S, so the number of elements in S is greater than 0, right? Uniqueness question is that whether it is greater than 1, and stability is, of course, basically whether xt converges to x star if at some t it is different than x star. Okay. So you can write a very simple example. Let me use a different color here. So you can write, for instance, a very simple example. For instance, this one, right? So this is now a dynamical system for just one variable. So it's just a single difference equation, right? So is there a steady state? Well, to find the steady state, basically you are looking at some x or x star that satisfies this equation. Okay, so from this you have x star square plus x star minus 9 equals 0. So this is a quadratic equation, and there is, of course, some solutions there, right? So then you can find such steady states. Okay. Well, uniqueness is, again, if you can find for a given f. So this is your f in this example, right? For a given f, if you find more than one steady state, if you have more than one x value that satisfies this equation, and in this case, if the roots are real, you're going to have something like this. So that's important. In general, we are interested in real valued variables. So you're going to disregard complex roots in such cases. But then you can talk about whether the steady state is unique or not as well, right? And stability, let me show you a general result about scalar systems. So stability can be understood in best way by using these phase diagrams. This is very simple, by the way. This is just undergrad material. So on the horizontal axis, we have xt. On the vertical axis, we have xt plus 1. Okay. Now, from a graphical point of view, steady state must be on this 45-degree line, right? So these are 45-degree lines. Okay. Each of them have slope equal to 1. All right. And for each, I mean, there could be, of course, different cases, but one case would be like this. Okay. Another case would be like this. Another case would be like this. And yet another case would be like this. Okay, now these are Fs. Okay. Here in this example, I am using a model where there's only one steady state, right? I drove them in this way just for simplicity. Okay. Now, what are the differences here? So these are again steady states, right? So what do I know about these states? Well, if you look at carefully, at this point, the derivative is okay. So that's poor drawing. So derivative is positive and less than 1. Here, derivative is negative and less than 1. Here, derivative is positive and greater than 1. And here it is negative, and in absolute value, it is greater than 1. Okay? Now, if the derivative is positive, the dynamics are non-oscillatory. Okay? So here the derivative is positive on the left panel at the top, and at the bottom the derivative is positive, so it is non-oscillatory. Right? And here the derivative is negative, so it is oscillatory. I will explain what this is. Okay? And if derivative in absolute value is between 0 and 1, on the top panel, on the left and the right, the derivative, the absolute value of the derivative at the steady state is between 0 and 1, right? So we call them stable. And if it is greater than 1 in absolute value, we call them unstable. Right? So this is about whether the slope at that steady state is between 0 and 1, and here whether it is greater than 1. Okay. For oscillatory versus non-oscillatory, here we have the derivative positive, here the derivative negative. Okay. Now, in the case of non-oscillatory movements, you have something like this. So suppose that this is x0. Okay. Then you find x1 here, right? So this is x1. Then this is x1, right? Then you find x2 here, right? So this is x2. Then your x2 is here, right? Then you find x3 here, okay? Then you find x3 here, exactly right here, okay? So as you see, convergence is non-oscillatory, right? If you draw it, you have something like this. If you draw it, you have something like this, right? This is T, this is X star. So there is no oscillation. Okay? So similarly, if you have x0 here, okay, so let's say this is x0, you find x1 here, so this is x1, right? If this is x1, you find x2 here, so this is x2. Okay, so as you see, you move away from the steady state, right? But again, in a non-oscillatory way, right? So you move like this. So this is the steady state, you are here, then you move away from the steady state. Okay. There's no oscillation, but if you look at here, let's say x0 is here. Okay. So if x0 is here, you go to the blue line and find x1, right? x1 is here. Then x1 is here. Okay. If this is x1, this one is x2, right? If this is x2, the red curve, so right here there is x2. Okay. And then you find x3 here. And that x3 is here. Okay. So you converge, because this is stable, as you see. So you converge in this way, right? So you converge like this. Okay. So it is oscillatory. Why? Because now you converge to the steady state. So let's say this is the steady state. Okay. You move like this. Okay. Against time. And here, let's say you start at this point. Okay. This is x0. Then you have x1 here, right? So x1 is here. So then you have x2. Okay. And that is here, right? So then you go up there. Somewhere the blue line is crossing with this one. So then you go there. So the red line goes there. And you find the blue somewhere here, right? So in that case, if this is the steady state, you move away from the steady state. Okay, because it is unstable, right? So what matters for stability is whether the slope in absolute value is between 0 and 1. What matters for whether the movement is oscillatory versus non-oscillatory, what matters is the sign of the derivative. Okay? So that's for the one variable case. All right? That's for the one variable case. Now, let me stop for a moment here. And so if you have any questions about these scalar dynamics, I can explain. Again, so you find the steady state, at least one of them is there, then you have an equilibrium. There could be, of course, more than one, right? Then you ask for each of these steady state, whether they're stable or not, then you look at the derivative of f function at these steady state points. If that derivative is negative, then convergence or divergence is oscillatory. If that is positive, it is non-oscillatory, but then you ask whether it is stable or not. For stability, you look at the magnitude of it, regardless of the sign. All right? So if the magnitude is in absolute value greater than 1, we understand that it is unstable. So regardless of the initial point, you diverge unless you are at the steady state at the initial point. And if it is between 0 and 1 in absolute value, then you converge to the steady state.
What is the meaning of the time if it is start from the -1 or -2? What is the economic intuition behind of this?
There is no definite economic intuition there. So time in these models is always a logical variable, right? Only when you take this model to the data, then you attach a specific meaning to time. All right. So if you, for instance, if you develop a model, if you construct a model with discrete time, and suppose that your model starts at -3, okay, t -3, then maybe you would be interested in, for instance, calculating the, some of these economic correlations, let's say, correlations among macro variables, 3 quarters before the crisis. Okay.
Okay. Then.
So then it would have a particular meaning because t equals 0 would be present quarter, right? Looking at the, I mean, imagine something like this. Sorry. So you can actually imagine something like this. So there are papers like this in the literature. So so this is t. Suppose that this is in quarters. Okay. You equate t equals 0 by the start of a crisis. Okay. And then you, for instance, look at the correlation between current account deficit and let's say, so this is your current account deficit divided by GDP, and then you look at the correlation of this with output gap. Okay. First, for instance, you look at a particular crisis. Okay. Then let's suppose that this is crisis 1. Okay. Then you look at, I mean, forget about this because it will not be factually correct. So there could be any correlation or any variable, right? Then you look at, I mean, suppose that you look at output gap, okay? You look at output gap, okay? So in one crisis, you would see something like this, okay? So this is, let's say, crisis 1. In another crisis, you would have something like this. In another one, you would have this. Okay? Then t equals 0 has a particular meaning, right? So then t equals -14 also has a particular meaning. So it depends on your, how you take your model to the data. Okay?
Okay, thank you.
All right. So if I continue with these scholar systems, let me show you one last thing, then I will start talking about the systems. You may have, of course, so this is xt plus 1 equals xt. You may have several steady states. Okay? Here you have 1, 2, 3, and 4 steady states. Okay? And depending on which, what is this variable, or what this variable is, what is the economic meaning of this variable, you may have different stories, right? So here I understand that this is stable, right? And this is stable, okay? But these are unstable, right? Then you may imagine, okay, if this is income or capital stock per worker, then here we have a low equilibria, right, which is stable. And here we have a high equilibria. So this could be a development problem. So you would start imagining how this poverty trap could be avoided. Then you can extend your model a little bit. You can tell me that, okay, so there is this possibility of a poverty trap because of these non-convexities in the production process. But then you can also tell me F could be also depending on, let's say, policy. Okay, policy at time t. At some level of, let's say education quality or productivity level, etc., you may have two steady states that are stable, but then at another level, you will have only one steady state. Okay, so here F is PT prime. Okay, so then you may imagine that, okay, some variable PT, this could be policy, this could be a shock term, this could be population, this could be productivity, education quality, whatever variable you are interested in. So then if that variable increases, then the dynamics change, right? Even under the case of non-convexity, there's no longer a stable equilibrium here. And the only stable equilibrium is here. Okay? So that depends on your context. That depends on your story. That depends on the theory you are working with. All right? Now, again, we are interested in two variable systems most of the time because we want to draw graphs, right? So what I write here is the general n-dimensional system. Let me just write it first. Okay, so here x is a vector, which is n-dimensional, and f is some function that maps Rn to Rn, or more specifically, we can define subsets. Okay, we can define subsets of Rn where the variable x is defined. So this is just a vector, right? So because I have, if I write it more explicitly, I have x1t plus 1 equals f1 x1t, x2t, xnt, right? So I have x2 t plus 1 equals f2 x1t, x2t, xnt, right? And that goes on. At the end, I have xnt plus 1 fn x1t, x2t, xnt. Right? So this is the general formulation, and also I can even write the system even more generally by writing this. But again, I will. So this would be a non-autonomous system. So when t is there, it is a non-autonomous system, but there's a way to make this system autonomous. All right, and I will show you that. Now, when we limit ourselves with n equals 2, then we're going to look at problems like this. All right, systems like this. Xt, yt, and typically we're going to assume that initial values are given. Sometimes, in some problems, we define these limits, okay, as steady states, and we assume that these are given. especially in the programming problems where transversality conditions matter, right? But in general, we're going to be working with initial conditions given. All right. Now, let me give you a couple of examples just to motivate what we're going to do. So I have about 6 minutes, so I can introduce at least one example. So you may imagine this. So let's say this is example 1. Okay. And this is a slightly extended version of a Malthusian model where we extend it with productivity. Okay, so let's say this is alpha minus delta PT. I will define the variables in a moment. And let's suppose that AT plus 1 is equal to gamma AT theta PT lambda. Okay, so we may suppose that alpha, psi, and delta between 0 and 1, beta greater than 0, gamma greater than 0, and theta lambda between 0 and 1. Okay, now this model is again a kind of a Malthusian model, a population model. So P is population here. Sorry. So P is population. Okay, and A is some measure of productivity or technology more generally. Okay, so what do we have here? Well, delta is the death rate. Okay, because there's a population existing at period t, so a fraction delta of these people die. And then there's also a birth function. Okay, so this is the total number of births. Now these births depend on productivity positively. Why? Because as in the Malthusian model, if there's a larger level of productivity, we have more income, we have better living standards, so we can afford marriage, we can afford having kids. And this depends negatively on the population level. Why? Because in the production process, there's diminishing returns with respect to labor, so land is in fixed supply. So if you increase the number of people working in the field, you increase total production, but marginal productivity decreases. So living standards then depend positively on productivity, but negatively on population. And then fertility or population growth depends positively on living standards. Okay, so that's the population, that's the movement of population. And productivity also evolves in this economy. So this is different than the textbook Malthusian model. So population evolves, productivity evolves in this way. So if you have more knowledge, or if you are already productive, so that explains your next period's productivity in a post-phase. So there's some persistence in technology, right? And then if you have more people are more creative. So you have more knowledge, or if you have more people, the markets are larger and firms want to expand their productivity level through innovation, etc., etc. So if you have more people, either you have a supply channel for innovation or a demand channel for innovation, so your productivity grows. Okay, so that's your system then, and you may of course assume that initial values are positive and given. Okay, now the first thing of course you're going to ask is whether there is a steady state, right? Then you're going to ask, is it possible that there could be more than one steady state? That's also interesting. And then for each of these steady states, you again ask stability. But stability now, since it is not a scalar system, you have to be careful with the dynamics in a system, right? And in a system, either you draw a phase diagram or you linearize the model in around one of these steady states, and then you look at the eigenvalues of the system. So that part is the same. And after the break, I will show you using this example and a couple more examples, how do you do each of these tasks, okay? So let me now stop sharing my screen. We have about 1 minute. If you have a very quick question, I can answer it. Or after the break, we're going to continue with solving such systems, finding steady states, drawing the phase diagrams, etc. Okay, then. Let's meet at 2:35. Is that good for everybody? 2:35?
Okay.
Right?
Yes.
Okay, because it will take around 15 minutes. So let's meet at 2:35. I'm ending this right now.